everyone, and welcome to today's Tech Skills Days talk. Today I'll be talking about how we can build a .NET 7 Raspberry Pi driven 3D printed robot arm, which is always good fun. A little bit about me first. My name is Pete Gallagher. Some folks might know me as Pete_codes on Twitter. I'm a full stack dev manager at Avande, as well as a Microsoft certified trainer, an Azure MVP, and I'm also a Pluralsight author, and I run a few meetups. I tend to focus in and around the IoT space, and I've been doing that since before the 2K line was crossed, so quite a while now. I'm also a dad to two young girls, and that drives me on to help children into STEM subjects, and especially minorities, where I think it's super important to make sure that everybody's got access to all of this cool stuff that we do every day. So moving on, today we'll be talking about how we can get this .NET 7 driven robot arm up and running. I won't dwell too long on the individual pieces, but we'll start out by taking a quick look at what's new in .NET 7, and then how we can get .NET 7 installed onto our Raspberry Pi. And then we'll start building up the various blocks of code that we need to be able to move from basically controlling the parts of the Raspberry Pi and onwards to interfacing out to the internet. We'll start out with the GPIO, general purpose input-output, and a really basic circuit for what will become then Hello World in the world of IoT. And onwards from there, we'll talk about device bindings and how we can drive servos. And then we'll quickly look at Blazor and SignalR, and then some final demos to round out the talk. And just before we carry on, I thought before we start, I'd show you what it is we're going to be building today. So if I switch over to a top-down camera that I've got, what you can see here is a 3D printed robot arm. So just here is the robot arm itself with a bunch of stuff holding it together. And then we've got a battery pack and a driver board, and then a simple circuit, and then a Raspberry Pi 4 here. The robot arm itself is made up of several different pieces, where we've got, the most important part we've got is these servos just here. They're like small motors with 180 degrees of limited motion, so they can move, in this case, forwards and backwards. And then we've got the gripper here, which moves in and out, and then one you can't see in the base can move left and right as well. So we've got rotation, reach, and then grip. These servos here, they're powered essentially by this servo board and then controlled by the Raspberry Pi over here. And then these batteries here, they're providing the power for these servos. I'll talk a little bit more in detail about how this all works in a little bit. But before we do that, let's flick back to the slides. So .NET 7, what's that all about? Well, this is a cross-platform development, an entire platform that allows us to be able to develop everything from desktop all the way through to AI. In that we've got the facility to be able to target not only regular desktop computers, but also things like the Raspberry Pi with its ARM processor, which is super powerful. There are a broad set of development tools available to us, of course, and I'll be using Visual Studio Code to do the demos today. What's new in .NET 7? Well, we've got ARM64 support. We've had that for a while now, which has been great for being able to make demos like this. But the support for ARM64 is becoming more and more mainstream, and they're really focusing in on performance improvements and adding cumulative fixes and improvements in that space for each of the releases of .NET recently. We've also got some improved system.text.json serialization. And we've also got some generic math, which means that we can do math without actually needing to know the types. So we don't need to add overloads for all our functions for all the different types. We've also got some regular expression improvements, where things are now optimized at compile time to make things run nice and fast. We've also got support for milliseconds and nanoseconds in time spans, which can be super useful for things like IoT. We've also got .NET new code completion, which I really like, because obviously with many installed templates, there's a whole heap of new .NET projects that you can spin up. So to have that code completion is really powerful. And we can also publish directly to a container now, which is great for being able to have like a hardware agnostic or platform agnostic development cycle there as well. So yeah, quite like that. So moving swiftly on to our Raspberry Pi. Installing .NET on a Raspberry Pi isn't as straightforward as just an apt-get, sadly. I mean, if you've got something like Ubuntu, that's okay. But for the Raspberry Pi OS installation that most folks tend to default to, then it's a little bit more involved to get that up and running. However, I've shortcutted that by creating a single line install script. So obviously go check out the contents of this script, don't just trust me. But once you're happy that you can run that, then you'll see that this installs all of the prerequisites we need to be able to not only run but also build on the Pi, which is great for beginning your journey into IoT with the Raspberry Pi. So once that's all up and running, you can see if you run a .NET info at the end, then it'll show you the versions of .NET that you've got installed. So we can see that that's .NET 7.0.1 on this particular GIF here. So moving on, the bulk of the work that we'll be doing will be through what's called GPIO, or General Purpose Input Output. And this is the way that the Raspberry Pi and the .NET that's driving it allow you to be able to interact with the outside world. So to do this, we'll be using a NuGet package called system.device.gpio. And this allows us to be able to not only drive the I/O, but also serial interfaces like SPI and I2C. And onwards from that, we'll also be able to drive things like PWM, pulse width modulation, which is actually going to help us drive our robot arm. But I'll circle back to that in a bit. This NuGet package supports a few different platforms, obviously Raspberry Pi that we'll be looking at today, but a few others like BeagleBoard and Hummingboard and Odroid. And it supports not only Linux, but also Windows 10 IoT, which, I mean, for me isn't really a thing anymore. It was a way of being able to get XAML onto a Raspberry Pi with a stripped down version of Windows 10, but for me there's far better ways of doing that with things like Uno platform that would drive me away from something like that. We can install that with the regular CLI or the NuGet package manager, of course. So GPIO, what's that? Well, along the side of the Raspberry Pi, there are a bunch of pins that we can connect wires and components to. It's important to know that there's two different numbering schemes for these pins. So there's the board numbering scheme that I tend to use because this just follows the numbers actually on the board, like the name implies. But there's also a BCM numbering scheme, which refers to the driver chip. So you can use either of these, and you're free to, but personally I'd recommend sticking with the board numbering scheme because you just count the pins on the device. And in fact, that top left pin that we can see in sort of the orangey colour there, or dark yellow, that square pin there is pin 1, then next to it is pin 2, and then we have 3, 4, 5, 6 that you can see numbered there. So it's relatively simple to follow that numbering scheme, so just stick to that. When you're going to begin any IoT journey, the first thing we want to do is flash an LED and read a button. And I've got a simple circuit down here that just exercises those bits for us. So if we zoom in on this, we'll see that on pin 10, we've got one side of the LED that goes through a resistor. This is a current limiting mechanism that must make sure that we don't draw too much current out of the Raspberry Pi and also put too much current through the LED, possibly damaging it. So pin 10 will be what we'll be using to turn our LED on and off. We've also got one side of a button connected to pin 26, and these two numbers will become valid and important when we start looking at the code in a minute. So we're outputting on pin 10 and we're receiving on pin 26 a button. So what we can do is we can have a look at our first demo. And again, this is in the world of IoT, this is what we call Hello World. And it really does just validate that we've got control over inputs and outputs. So if I switch across to the terminal that I've got here, just before we get going, if we do a .NET --info, we'll see here that we've got a few versions of .NET installed on this Pi, but more importantly, we've got version 7.0.202 installed on here. Now I'm in the directory where I've got some code, and that code is shown here. So I'm not going to spend a great deal of time going through all of these bits of code, but I do want to at least highlight this in the beginning so we can see how it's built up. You can see here that we're bringing in the system.device.gpio NuGet package. And that, again, is going to do a lot of the heavy lifting of driving the inputs and reading the outputs of all of these demos, actually. A bit further down, you'll see here on line 12, actually, that I've got a console.write line for hello world, and I tend to leave this in. Because if something goes wrong and it doesn't run properly, then you've got an idea that actually the application's running. So even if you've wired it up wrong, you know that it's probably your fault rather than the code. So that just tells me that the code's ready and up and running. It's a little bit more important when we start reading buttons, because we'll need to know when it's ready to read the button. I could put something more descriptive, but this is fine. The next thing we do is we create a GPIO controller instance. And if you remember, we spoke about the fact that there can be two different numbering schemes, board and BCM. Well, here we're passing in the pin numbering scheme of board. So that's where that becomes important. Next up, we're creating a variable for our pin. This is just going to drive an LED. And then once we've defined that, we can use the controller to open that pin, and we're going to set it as an output to be able to drive the LED. Onwards from that, we just create a basic loop in a try-catch here, and we, using a thread sleep in between, which we're setting to 300 milliseconds here, we set the LED to high and then to low, and then we just loop like that forever. And at the end, we simply close that pin so that we release that pin back to the system. So let's run that and make sure that we can see what it does. If we do .NET run. Now, on another screen here, I've got a webcam pointed down at this, an Ocio cam. And so we can see here now that this is the robot arm that we'll be driving in a bit. And there we can see the LED flashing away to itself happily. So that really is your Hello World, or at least the first version of Hello World. And that proves that we're able to write some code and interact with GPIO. But we also want to make sure we can read an input as well. So let's do that. So if we stop that, clear the screen. If we switch back to this code, I'm not going to write any code in this. I'm just going to switch between Git branches because I'm nowhere near that brave. So if we switch to the read button branch, and there we are, that's read in. Nothing at the top has changed pretty much. We're all pretty much the same all the way down through to setting up the LED pin. But we're now defining a button pin, and we're making that a pull-up here, so an input pull-up. And what that means is that we don't need a resistor to be able to pull that line to a specific level so that when I press it, we know it goes to another level. This is just a bit of electronics trickery just to make sure that we can keep the number of components down, but it kind of simplifies the circuits here as well. If you don't do that, it'll kind of float around and you can't guarantee that you're going to get that button to work. So do bear that in mind. Next, you'll see here, because of the way we're pulling this up, so what that means is when it's not pressed, it's pulled high. Actually, when we press the button, it'll pull it low, so we'll get a false. So it'll kind of feel a bit backwards, this code. So when that button line is false, it's pressed. So at that point, we set the LED to be on, otherwise we set it to be off. And then we close that LED pin again. So let's run that one. And then we can switch across to the circuit, and we'll see the LED disappear off when our little program starts. And there it is. And so now if I press the button, we'll see the LED comes on, and if I release it, the LED goes off. This is a really expensive way to connect an LED to a button, but actually what we've done now is proven that we can control both outputs and inputs here. We can read that button and we can light that LED up. So that's really us starting our journey quite nicely now. So let's stop that code. There we are, clear the screen again. If we switch back to the slides, the next thing we're going to do is talk about how we can control what's called the servos, the little motors that are moving our robot arm around. And of course, one of the things that we should always do is use somebody else's code for that. And so nicely, somebody's created a NuGet package called iot.device.bindings. And this is a collection of maybe 25 or 30 different devices that code has been written for to work with .NET, for a bunch of different peripherals. Now, there's ones for temperature and humidity sensors, and me and my good friend Cliff Aegis, we're often joking about that is the next step quite often for folks in their IoT journey, but it's very boring. And it's not very interesting to show to folks either, because we're having to breathe on a temperature sensor and watch it go up, and it takes forever, and it's just not a very interesting demo. So that's why I tend to focus on things that are a little bit more interesting, like robot arms. We can also drive things like I/O expanders, because obviously we've got limited inputs and outputs on the Raspberry Pi, and this allows us to be able to drive and read more. There's things like the Explorer hat and the Sense hat, which are hardware attached on top of the Raspberry Pi to give it some extra functionality. And we can also drive servos, which is the important part for our code. So if we move on to the next slide, this next circuit, which you'll have seen part of when I switched to the webcam above, will allow us to be able to, through a driver board, drive 3 different servos, 3 different motors, which I'll talk about shortly. Looking at the circuit here in a bit more detail, you can actually drive these servos, these little motors, directly from the Raspberry Pi, but you risk burning pins out because they take quite a lot of current, certainly if they stall or at startup. So I'd recommend that you use something like this board, this Servo 6 board. So the control part, that's just done with the Raspberry Pi, but the power side is then driven by some batteries, and that just ensures that it's the batteries taking the load of the power rather than the Raspberry Pi. So looking at the circuit here in a little bit more detail, on pin 25 we've got ground, and that's fed to that far right hand side pin. And if you do buy this Servo 6 board, just bear in mind that that ground pin is kind of labelled over to one side. So that is the first pin, ground. Next up, we've got pin 35, which I'm using to drive the rotational servo motor. Then I've got pin 13, and I'm using that to drive the reach, as it's called. And then I've got pin 12. And actually, we'll find that there's only 2 hardware pulse width modulation ports on a Raspberry Pi. And actually, this is a software-driven port that is part of that IoT device bindings NuGet package, and I'll talk about that again in the next part. So if you've not seen what servos are, so these are tiny little motors that tend to have 180 degrees of freedom, and they work using something called pulse width modulation. So this is, in very simple terms, if you imagine that you've got a small short pulse with a big gap in between it, if you feed that to the servo motor, then the servo motor will move one way. If you've got like a regular sized pulse and a regular sized gap, then it'll move to the middle. And then if you've got a long sized pulse and a shorter gap, then it'll move to the other side. And this is constantly being fed to the servo motor to keep it sort of in place. So it sort of floats to that position and then sticks there so long as you're still sending that same pulse width modulation. So that gives you a basic idea of how these servo motors are actually working and how we're moving things around. But we don't want to have to write the code for that. So that's why we use things like the device bindings NuGet package. So let's have a look, and we'll make our robot arm move, and I'll show you what that code looks like. So switching to our move servos branch, just here, and if I scroll up, pretty much everything's the same at the top, only now we've got the PWM and drivers, and we're also pulling in the IoT device servo motor here. So this device.pwm and the drivers part, they're coming from the system.device.gpio library. So that's where this is coming from. So PWM is built into that, but actually driving a servo motor is a little bit more than just having PWM control. We need to convert frequencies and the like to individual angles, and that's what this NuGet package is giving us a facility to do. So a little bit further down below our hello world, we first create a PWM channel, and that's going to be coming again from the system.device NuGet package. And next we create a servo motor, and that's coming from the IoT device bindings NuGet package. For this create, we pass in 3 different parameters. The first is the chip number. The Raspberry Pi's only got the 1 chip, so you'll see both of these have got the same 0 in here. And then we've got the channel number that we'd like to use, and there are 2 hardware channels on the Raspberry Pi. So this first one is 0 and the second one is 1. And then we just pass in this frequency part here and just leave that at 50. Next up, we create the servo motor and we pass in that PWM channel for that particular servo motor. We tell it how many degrees of freedom it's got. In our case, that's 180. And then a minimum and a maximum frequency here as well. And then we do that again for the second servo motor. So these two are controlling the rotation of the robot arm and also the reach part of the robot arm. And then we've got a software PWM channel. So as I said, there's only 2 hardware PWM channels that the Raspberry Pi's controllers will actually help to run. And when you run out of those, you've got to use a software one. So the IoT device bindings folks that have created that code have actually given us a nice software-controlled PWM channel. So we tell it which pin to work on and the frequency. We also tell it here to work in a high accuracy timer mode. If you don't do that, you get a very jerky response. If you imagine the Pi's got to control the whole operating system, so timing functions are actually hard for a real-time system to work on top of an operating system. So that true that we pass in will ensure that we're in a high accuracy mode. And then next we just pass it into a regular servo motor like we would any other PWM channel. And so now we've got the gripper, as it's called. So at that point then, we start up those 3 servo motors. And then next up, we've got a loop here that we're just making it dance. So what it's going to do, it's going to exercise each of those channels, moving them to and from different positions, just so we can see it moving. So it's a very wobbly robot arm, this. I've not made it perfect. It's not meant for that. It's really just meant to demonstrate what it is. So let's flick to that and see how that works. So if I run this one, and then we switch over to our webcam, and when that runs up, there we are. So we've got it moving. There we are. So we can see each of the individual pieces of our robot arm now are moving away happily. So that's great. So we're quite happy with that. So now that that's running, we can stop the code and we can move on. Right, so if we clear that screen and go back to our slides. So the next part is Blazor. And I'm not going to spend too much time on these individual pieces, but Blazor is a single page app framework for building interactive website .NET applications. And it allows us to be able to get rid of the JavaScript element to a degree out of our applications and create entire single-page applications just using the power of C#. And so I decided to use this to be able to drive my robot arm. What I wanted was a way that I could drag sliders around and have the robot arm move around its degrees of freedom. So that's what that's for. Now, if anybody knows me, you'll often find me talking about IoT hubs and the like. Well, actually, I could use IoT hubs here, but what I wanted was a real-time control. And SignalR allows us to do that in that it's a library for ASP.NET developers to be able to add real-time web functionality to their applications. So with the power of WebSockets, we can create a hub, as it's called, a central point, and then connect our application up to that hub. And then have that communication have a real-time communication link between our website, if you will, and the controller here on the Raspberry Pi. So let's add that to our repertoire here and show how that one's working. So what I'm going to do is switch out to our main branch here, so no more switching after this. And I'm not going to spend a great deal of time talking about how the individual pieces of this are working. But what I will do is just give you a brief overview of how we're connecting our Raspberry Pi out to a SignalR hub. So everything at the top of this is identical in that we're creating the 3 different PWM channels and servos. But next we create a connection, and this is our SignalR connection here. And we're connecting this out to the IP address of my local machine here, which I'm going to run the Blazor application on, that's also going to host the SignalR hub. And we're calling it a chat hub here. Now, if you've ever done any SignalR work, then the likely first application you'll have made will be a chat app. So that kind of alludes to where this code comes from. We also do this dangerous accept any certificate, which is just a way to get over the fact that there's not a certificate that's valid on my local machine for the Raspberry Pi. Don't do that in production, obviously. And then we have an automatic reconnect in case it fails, and then a build. Now, I mentioned that a chat app is where you base a lot of your code on for SignalR, and that's kind of what I've done here, just to show the steps. And we make a quick change, and we point this to we've got a user and a message, and the user version will become the servo, and the message will become the angle we want to move it to. So then I just parse through here, and if any of these are servo 1, servo 2, or servo 3, then we move that servo to the angle in the message. And then that's it. And then at the end, we just stop. And then just a simple routine just to make things a little bit easier. So let's run that. And so with that running, we can switch over to our application, our Blazor application. And we can see on the left-hand side our robot arm. So on the right-hand side here, we've got a Blazor application, and we've added some SignalR goodness to it. And what happens is that every time I move these sliders, it sends a message through that SignalR link to the Raspberry Pi, telling it which servo to move and the angle to move to. So if I move this slider across, we'll see that the robot arm happily moves from side to side. It's very jerky, of course, but we're happy enough with that. And then this one here will move the robot arm forwards and backwards. And this one here will do the grip that you can see at the front, and that's the software controlled one. So that's really nice, I like that. But of course, now that we've got a Blazor application, we should really deploy that to Azure. And that'll give us some extra facilities as well. So if we go across and stop our application again. And then we run that one. And then switch to this tab. And then what we've got in here is a live video feed built into the web page just to make it slightly easier. And then we can see that if we do the same things, we can rotate our Raspberry Pi robot arm from here and adjust the reach and the grab. Just the same as we could before. But now that we've done that, that means that this is now a publicly accessible point that we can connect to. So as long as we've got the correct authorization, we can actually drive this from any point. Which means that we can, in theory, use something like an Oculus Quest to do this through VR. So let's have a look and see how that works. So returning to our slides, what we're going to be using is something called Unity. And Unity is a cross-platform game engine. And it gives users the ability to be able to create games and experiences in both 2D and 3D, but using .NET, which is fantastic. And so let's switch over to our final demo and see how we can drive our robot arm using an Oculus Quest 2. So if I switch over to this screen here, then on the left-hand side, I'm casting from my Oculus Quest 2. And on the right hand side, this is the web deployed version of our SignalR based Blazor application. So what we're able to do is move our Raspberry Pi robot arm using a VR app connected to the same SignalR hub that's in Azure now. So let's have a look how that works. So excuse me, I'm going to put my Oculus Quest 2 on. And then here we've got some sliders on the left and what is a robot arm on the right hand side. So if I I can click on anywhere on here and I can rotate my robot arm left and right, and we can see that the robot arm in the VR world is moving at the same time. And in fact, were I to try and control the robot arm from the web, it would also move here in VR. So the two things are directly connected. Likewise, I can move the reach forwards and backwards, and I can control the gripper as well. So we can see that that's nicely moving there, although there's a bug in my app that means it doesn't move in VR when I do that, sadly. So yeah, so now we're controlling a robot arm from virtual reality, all with the power of SignalR and .NET. So very good. So switching back across to our slides for a final few slides. This wasn't plain sailing the whole way through. It turned out that my cat liked these servos, so the cat would jump up and start playing every time I was developing this particular talk, which was funny. And it's a wobbly robot arm, and does some funny things when you start moving it around, of course. Bit wobbly. And it gets so wobbly, in fact, that if you do the wrong thing at the wrong time, then it'll just go and fall over. So yeah, these things are never plain sailing when you're doing them, but I just thought it was worthwhile showing you some of the things that happen along the way while you're developing, certainly with hardware. So here's some links. You don't have to worry too much about taking a note of those, because there'll be a link to the slides at the end anyway. But you can see there that actually there's all of the code for this is on GitHub, and there's a workshop to build your own version of this too. So do check that out. And then there's some more information about .NET and the device bindings and where you can find the 3D printer files for this particular robot arm. I mentioned earlier that I run a few meetup groups, and they're listed here. So Knots IoT, .NET Knots, Knots Dev Workshop, and Lati. I'm also part of the Agile Engineering podcast and also the Azure-ish Live Twitch channel. If you want to get in touch with me, Twitter's often the best place. Just drop me a DM on @Pete_codes and ask me any IoT question you like. I'm happy with that. Alternatively, you can email me there at pjgcreations.co.uk. And do feel free to go check out my blog there at petecodes.co.uk. If you scan that QR code, that'll take you to these slides, so don't worry too much about not getting down those links. They're all contained in that slide deck there, so do feel free to go and check that out. And with that, thank you very much for watching, and I look forward to seeing you again soon. Cheers.